In the world of computing, systems rely on the seamless interaction of processes to achieve remarkable feats. But what happens when these processes clash, bringing everything to a standstill? We have the expertise and solution to break free from the grip of deadlock. Join us as we explore an innovative strategies and cutting-edge tools to ensure your system runs smoothly, efficiently, and without interruption. In a multi-programming system, processes request resources. If those resources are being used by the other processes, then the processes enter in a waiting state. So what is deadlock? Deadlock is a situation in computing where two or more processes are unable to proceed because each is waiting for the other to release resources.
Look at the diagram above. This diagram illustrates a deadlock situation where process 1 and process 2 are each holding one resources and waiting for the other to release the second resource, creating a circular dependency that prevents both processes from proceeding. For example, traffic jam at an intersection. Imagine two cars at an intersection where each car needs to pass through the other lane to proceed. Car A is in lane 1 and needs to move to lane 2, while car B is in lane 2 and needs to move to lane 1. Both cars are waiting for the other to move first, causing a deadlock where neither car can proceed. By looking in the diagram above, this diagram shows a deadlock where process 1, process 2, and process 3 are each holding one resource and waiting for another, creating a cycle that prevents all the processes from proceeding. For example, traffic jam at an intersection. Imagine three cars at a three-way intersection, each needing to move into the lane currently occupied by another car. Car A needs to move to car B's lane. Car B needs to move to car C's lane, and car C needs to move to car A's lane. All cars are stuck waiting for the other to move, causing a deadlock. This example mirrors the deadlock in computing, where processes are stuck waiting for each other to release resources, leading to a standstill.
Understanding the conditions for deadlock. Number 1. Mutual inclusion. Two or more resources are non-shareable. Only one process can use it at a time. Means that at least one resource must be non-shareable. In simple terms, only one process can use this resource at a time. For example, imagine two people trying to use the same printer, but only one can print at a time. Hold and wait. There must be at least one process that is holding at least one resource and waiting for other resources, that one being held by other processes. Means a process is holding onto one resource while waiting for another. Number 3. No preemption. A resource cannot be taken from a process unless the process releases the resource. In this condition, a resource cannot be forcibly taken away from a process. The process must release it voluntarily. For example, it's like you borrow a book from someone. They can't take it back until you decided to return it. Number 4. Circular wait. A set of processes waiting for each other in circular form. This is when multiple processes form a cycle where each one is waiting for a resource held by the next process in the cycle.
There are three types of deadlock. First is resource deadlock. It occurs when the processes are waiting for resources that are held by other processes in a circular fashion.
For example, if process 1 has resources R1 and R2 and requests resources 3, it will not proceed until it has all the three resources.
Second is communication deadlock. It arises when the processes are waiting for the messages or signals from other processes in a circular manner.
For example, in a distributed database system, three servers are involved in a transaction. Server A sends a request to server B and waits for a response. Server B sends a request to server C and waits for a response. And server C sends a request to server A and waits for a response. In this scenario, each server is waiting for a response from another server, creating a circular wait condition. As a result, none of the servers can proceed, leading to a communication deadlock.
Third is scheduling deadlock. It happens when the processes are waiting for a particular schedule or sequence of events that can never occur.
This can happen when not enough resources are allocated to a process or when processes are caught in a loop of waiting for each other. For example, 4 people at a round table, each person has 1 fork but needs 2 to eat. If everyone picks up the fork to their left and waits for the fork to their right, no one can eat.
Resources allocation deadlock. First, request resources. Processes request resources from the operating system complete their tasks. Example, web browser. When you open web browser and enter a URL, it becomes a process that needs to request various resources from the operating system to function. The example, CPU time, memory, network device, file system. Number 2, allocate resources. The operating system allocates the request resources to processes. Example, an operating system or OS acts as a resource manager, allocating and delocating resources to different processes. This ensures that multiple processes can share system resource efficiently and prevents conflicts. The third, deadlock condition. If the 4 necessary conditions for deadlock are met, the system can enter a deadlock state. Example, a deadlock occurs when 2 or more processes are stuck in a waiting state, each waiting for resource held by another process. This creates a circular dependency where an process can proceed because it's waiting for a resource that another process is holding, which in a turn is waiting for resource held by the first process. And the fourth example of 4 necessary conditions for deadlock. Number 1, mutual exclusion, hold and wait, no preemption, and circular wait.
Methods of handling deadlock. First, deadlock prevention. Second, deadlock avoidance. Third, deadlock detection. And fourth, deadlock recovery. Deadlock prevention. In deadlock prevention, the aim is to not let fulfill one of the required condition of deadlock. This can be done by this method. First, the mutual exclusion. We only use the locks for the non-shareable resource, and if the resource is shareable, like read-only file, then we not use the locks here. Hold and wait. To ensure the hold and wait never occurs in the system, we must guarantee that whenever process requests for the resource, it does not hold any other. Third, no preemption. If the process is holding some resource and requests other resource that are acquired in this resource are not available immediately, then the resource that current process is holding are preempted. After some time, process again requests the old resource and the other required resource to restart. Circular wait. To remove circular wait in the system, we can give the ordering of the resource in which a process need to acquire. Third,
the deadlock detection. Deadlock detection is the process in computing where the system checks if there are any sets of processes that are stuck waiting for each other indefinitely, preventing them from moving forward. Deadlock recovery. If deadlock prevention or avoidance is applied to the software, then we can handle this by deadlock detection and recovery, which consists two phases. In the first phase, we examine the state of the process and check whether there is a deadlock or not in the system. If found deadlock in the first phase, then we apply the algorithm for recovering the deadlock.
Methods of deadlock recovery.
There are several deadlock recovery techniques. Manual intervention. When a deadlock is detected, one option is to inform the operator and let them handle the situation manually. While this approach allows for human judgment and decision making, it can be time-consuming and may not be feasible in large-scale systems. Process termination. Abort all deadlock processes. This approach breaks the deadlock cycle, but it comes at a significant cost. Abort one process at a time instead of aborting all deadlock processes simultaneously. This strategy involves selectively aborting one process at a time until the deadlock cycle is eliminated. Resource preemption. Selecting a victim resource preemption involves choosing which resources and processes should be preempted to break the deadlock. Rolling back the process to safe state and restarting it is common approach. Starvation prevention. To prevent resource starvation, it is essential to ensure that the same process is not always chosen as a victim. Deadlock ignorance. If a deadlock is very rare, then let it happen and reboot the system. This is the approach that both Windows and Unix take. In deadlock, ignorance performance is better than the above two methods, but the correctness of data is not there. Safe state. A safe state can be defined as a state in which there is no deadlock. It is achievable if a process needs an unavailable resource. It may wait until the same has been released by a process to which it has already been allocated. If such a sequence does not exist, it is unsafe state. All the requested resources are allocated to the process.
The difference between deadlock and starvation. In terms of their definition, deadlock is a condition where two or more processes are blocked forever, each waiting for a resource held by another, while starvation, a condition where a process is perpetually denied necessary resources despite resources being available. In terms of resource availability, deadlock resources are held by processes involved in the deadlock, while starvation, resources are available but are continuously allocated to other processes. In terms of cost, deadlock circular dependency between processes which each process is waiting for a resource from another, while starvation, continuous preference or priority given to other processes causing a process to wait indefinitely. In terms of resolution, in deadlock, it requires intervention such as aborting processes or preempting resources to break the cycle, while in starvation, can be mitigated by adjusting scheduling policies to ensure fair resource allocation.
Ways of handling a deadlock. Number 1. Process termination. To eliminate the deadlock, we can simply kill one or more processes. For this, we use two methods. Number 1. Abort all the deadlock processes. Aborting all the processes will certainly break the deadlock but at a great expense. This means killing every process involved in the deadlock. While this guarantees the deadlock will end, it comes with a high cost as all progress made by those processes will be lost. Number 2, abort one process at a time until the deadlock is eliminated. abort one deadlock process at a time until the deadlock cycle is eliminated from the system. In this approach, we terminate one process at a time and check if the deadlock is resolved. We continue this until the deadlock is cleared. This is less disruptive than aborting all processes but takes longer to resolve. Number 2, resource preemption. To eliminate deadlocks using resource preemption, we preempt some resource from processes and give those resources to other processes. These methods includes two case steps. Number 1, selecting a victim. We must determine which resources and which processes are to be preempted and also in order to minimize the cost. Here we decide which process or resource should be preempted, and the goal is to minimize the cost of preempting. Number 2, rule back. We must determine what should be done with the process from which resources are preempted. One simple idea is a total rollback. That means aborting the process and restarting it. After preempting resources, we might need to roll back some processes to an earlier state so that they can restart without causing deadlock again. Number 3, starvation. In this system, it may happen that the same process is always picked as a victim. As a result, that process will never complete its designated task. Starvation occurs when a process repeatedly gets chosen as a victim in the process of resolving a deadlocks. As a result, this process may never get the resources it needs to complete the task. Number 3, priority inversion. A technique for breaking deadlocks in a real-time system is called priority inversion. Priority inversion is a technique used in real-time systems to manage deadlocks. Number 4, roll back. In database systems, rolling back is a common technique for breaking deadlocks. Resource allocation graph, RAG for deadlock detection. The resource allocation graph is a popular technique for computer system deadlock detection. The RAG is a visual representation of the processes holding the resource and their current state of allocation.
Several approaches to detecting deadlocks in an operating system. First, resources allocation graph. This method involves constructing a graph that represents the resources and processes and then analyzing the graph to check for cycles. A visual mathematical way to determine if a deadlock has or more occurred. G equals VI and VE. The graph contains nodes and edges. V nodes consist of processes equals to P1, P2, P3, and resources types are R1, R2. Easy edges are PI and RJ, or RI and PJ. An arrow from the process to resource indicates the process is requesting the resource. An arrow from resource to process shows our instant of the resource has been allocated to the process. A sample of the resources allocation graph. Consider a system with two processes, P1 and P2, and the two resources R1 and R2. Second, the deadlock condition algorithm. This algorithm periodically checks the resource allocation status and resource request to identify circular weight condition. A sample of deadlock condition algorithm. Consider a system with three processes is P1, P2, and P3, and the two resources types are R1 and R2. Number 3, Bunger's algorithm. This algorithm uses a mathematical model to determine if a state is safe or unsafe, considering the maximum resource need available resources. Example, it simulates the allocation of resources to processes to ensure that the system remains in a safe state.
In conclusion, Recovering from a deadlock in an operating system involves detecting the deadlock and then resolving it by either terminating some of involved processes or preempting resources. This action help free up the system and restore normal operation, though they may cause temporary disruption.
Thank you for watching.